Hello, welcome to probably the last playthrough of the complex number game. As you can see, we're starting on level 4, but maybe I should go through what we've been doing, just very briefly, go through what we've been doing in levels 1 to 3. If I put that like that, yeah, you see, so far I've solved levels 1 to 3, and whatever's going on. Let's put that back because it completed. Yeah. So there we go. So far, everything's broken. Everything's broken. That's what the problem is. And so let's restart lean. And hopefully those yellow bars will disappear and things will no longer be broken. Right. So that's what's supposed to happen. So let's start. Let me briefly go through what we've done before. So what have we done before? We did this very basic level that defined the complex numbers, and it proved they were a ring. This was the main thing we did here. We proved that the complex numbers were a ring, and so that involved defining 0, 1, addition, negation, and multiplication. No, we didn't define division. We just did everything necessary for a ring. So there we proved the complex numbers were a ring, and then last week we defined the map from the reals to the complex numbers and proved all the basic facts about that. And we also defined the complex number I, the square root of -1, and we also defined, you see I could show you the solutions. We may as well look through the solutions. Here's I, here's my official solutions to I. There you go, I define I to be the complex number with real part 0 and imaginary part 1, and there's some simple lemmas that we proved about I last time. And finally, complex conjugation. This was the last thing I did last time. We defined complex conjugation. There's the definition. The complex conjugate of a complex number is the thing with real part the same and imaginary part the minus. And we proved various lemmas about complex conjugation, some of which don't seem to be here so far, but it doesn't matter. So now today we're going to do norms. So the norm of a complex number involves a square root, and so instead of making things complicated by adding the square root, we're just going to do squared norms. So we're going to define the squared norm of this complex number, and the point is that the norm of this complex number is going to be a real number, you see. So it's going to be the real part. Well, let's do this. Here's a bad way to define it for reasons that will become apparent later. Read z squared plus imaginary z squared, right? If z is a complex number, then its real part and its imaginary part are real numbers. And what I'm attempting to do is I'm attempting to define a real number, re z squared plus imaginary squared. So re z and im z are real numbers, and the reals are a field because we've imported the reals and all the facts that we need to know about the reals. So this is a real number. And this is a slightly problematic definition, actually, quite surprisingly. Because how are we going to prove this? So I'm going to change that definition in a minute of this norm square. How are we going to do this? You know the deal. We want to check the real part and the imaginary. No, this is a real number. This is, let's just simplify it. Let's try this. Let's see what the simplifier does if we just tell it norm square. And the simplifier doesn't manage to solve this very, very easy lemma. It didn't manage to solve that the norm squared of 0 is 0 because the simplifier can't solve this. That's as far as the simplifier got. It got as far as 0 squared plus 0 squared is 0. And the simplifier happens not to know that 0 squared is 0. So it got stuck. And what's happened here is we could have made this definition a bit simpler, right? Instead of squaring, we could have multiplied it by itself. So mathematically that's the same, but as far as computer science is concerned, that's a more primitive function somehow. What have I done wrong? That. So if we define norm square to be this, re times re plus im times im, then we're somehow using simpler tools, and the simplifier can handle them better. So the simplifier can now prove this. So we can just do by simp norm square. There. And so similarly here, I'm expecting the simplifier just to be able to do this by simp norm square. There, we don't need anything about extensionality. because remember these are assertions about real numbers. So again, by simp norm square. You have to put norms. If you don't put norm square in, like if we just try by simp, then it just gets stuck at the very beginning. It's like, okay, so it's some question about norm square, and I don't have anything in my armory about norm square really. So this says, honestly, it's all right, unfold it. There, just to show you what's going on there. If I do print prefix, this is actually quite interesting. Just after this definition norm square here, you can kind of see, I think some more things appear. If I print prefix norm square, there, then what actually happens now, we get nothing. So I don't know, I'm quite surprised that I don't really understand how this works. I thought there'd be some weird equation then or something. Anyway, so the simplifier is just solving these once we tell it to unfold. This is basically telling it to unfold norm square. So how are we going to do this one? So this is all going to be, let's try this. By simp norm square. Ah, and it hasn't worked. Why has it not worked? Ah, it hasn't worked because you can see what the goal is here. The simplifier's made some progress, but the simplifier's got stuck, right? The simplifier has failed to solve this goal here. And this goal here is just some stupid statement about equalities of real numbers. It will just be easy. It will just follow from the axioms of a ring. So I'm going to put ring here, and that should pwn it. Yes. In fact, I'll write it this is the way I'm supposed to write these arguments nowadays. There. I could have used begin end because I've got two tactics. When you've got one tactic, you can just use by. I need two tactics here, but I've used by anyway. So how are we going to do this one? By simp, let's try by simp norm square again. What does it even say? What's the point of even reading it? By simp norm square. Oh, actually, this might be quite tricky. No, by simp norm square, this looks like it should be true. This is, again, an identity in the theory of rings. And the real numbers are known to be a ring, so I should be able to do this. Yeah, so again, that solved that one. What about this? The norm square of minus z is the norm square of z. Again, that we might have to use ring. Let's use simp norm square. See how far it gets. It solved it because you see we have no errors down here. Norm square conj. So this is easy, isn't it? Well, yeah, I could make norm square have attribute reducible. Then I might not even have to do that. Do you want to try that? I'm just scared it might break things later. Someone in the audience is suggesting I make norm square reducible, and I think if I do that, then it. Oh no, it still doesn't work. Yeah, I don't really understand the reducible tag. I'm going to take it away because Patrick Masso once told me, if you don't know what you're doing, then don't make definitions reducible. So I think I'm going to leave it like that. So this should be, oh no, not by simp norm square. No, by simp norm square has been fine. It's kind of difficult to tell, isn't it? If I put a semicolon or a comma. No, I don't know. We can just check the errors and observe there aren't any. So this should be fine. This just boils down to the same with r times r plus 0 times 0 is r times r. Yeah, the simplify can do that. Let's try this one. Now this is a question about complex numbers. Z times conj z. If you think about it, this left-hand side is a complex. What does that actually mean? Let's have a closer look at this one. Z times conj z is norm square z. If you look at the goal, you have this little up arrow here. And that little up arrow means, oh yeah, something slightly funny is going on. We've got some invisible map. We're pretending that something has one type when it actually has another type. And z times conj z, when you think about it, z and conj z, these are both complex numbers. So the left-hand side is a complex number, and the right-hand side is a real number. And what's happening is that real number is being coerced into the complex numbers. So we're going to have to start this one with extensionality. There, if we start with extensionality, we can kind of see there's that's two goals about real numbers. And now we could try the simplifier and see what it makes of it. So the simplifier doesn't know anything about norm square. So let's tell Let's tell it to unfold the definition of norm square. And now what have we got? We've got this lemma here. So that was just too much. You see, this is kind of trivial from the axioms of a ring, but it was too much for the simplifier. So let's use the ring tactic instead. So there you go. That's proved that theorem. So we're kind of zooming through this. We're 13 minutes through, and I've just kind of completely pwned a whole bunch of this stuff with trivial tactics that are there already, because we've got the simplifier, which does all the unraveling, check by unraveling it into pieces calculations. And we've got ring, which checks all identities in rings, and we know that the complexes and the reals are rings. So these are the tools we've got so far, and they're working quite well. But now suddenly here, right at this point, it all goes pear-shaped. So this is the hardest part of this walkthrough, because these innocuous-looking last 5 levels here, they are not what you expect somehow. Have Patrick guessed? Yeah, Patrick's brilliant. I should ask Patrick to stream. He might give it a go. He's got a headset, I know that. I was talking to him 2 days ago about his IAS talk, and he was wearing a headset. So I'll show you what the problem is. Let's try and prove this. So we're trying to prove something about Z. Let's do cases Z. Let's just break it up into cases. This is a question about real numbers, right? Norm square is a real number. This is a question about real numbers, and Z is a complex number. So let's do cases Z with X and Y. And now let's try and cheer that up a bit. No. Oh, now let's simplify it. There. So now we can see what the question really is. Right, what this is a lemma about a complex number, but what this question really is to prove this statement here. If X and Y are real numbers, then X squared plus Y squared is at least 0. And how do you prove inequalities in lean? We've got this linearith tactic, right, which is really good at proving inequalities. And it doesn't work. And why doesn't it work? It doesn't work because linearith does linear stuff. And we've got something that isn't linear here. We have some quadratic situation, and so linearith doesn't work. So now we're kind of out on our own, because this has got nothing to do with the complex numbers. This is just some lemma we need. This is some lemma we need from the theory of real numbers, and there should be some kind of the theory of this is complete, right? There should be an algorithm which solves this, but the algorithm hasn't been implemented into lean, and so we have to prove this by hand. So how would I prove this by hand? I would apply add non-neg or something, I guess. You see, I'm having to work out what the names of lemmas are. Yeah, add non-neg says that if A is non-negative and B is non-negative, then their sum is non-negative. So if I apply add non-neg, now I've got 2 goals. I've got to prove that X squared is greater than or equal to 0 and that Y squared is greater than or equal to 0. And again, these have names. You see, this is apply. What was it called? It's called mul self non-neg. Right? You can see these on a good day with the following wind. Here we go. There, you can see various suggestions when I type mul self. And there's the one I want, mul self non-neg. For all A, 0 is less than or equal to A times A. So if I apply that, it kills one of the goals. And if I put a semicolon there, then it applies to both of them. So there I proved norm square non-neg, but it hurt. And so what's happening here is that I shouldn't be proving, these are lemmas about complex numbers, I shouldn't be proving intermediate interesting theorems about real numbers whilst I'm in the middle of proving something about complex numbers. So we need to find the kind of the missing code, and hopefully I've got this here. What I think the missing code is, I haven't got it here. Which means I might have to look on my laptop. Just give me 1 second. I formalized a few lemmas purely about real numbers, but non-linear inequalities. And I decided that they were worth proving independently. So let me just copy these 5. I wonder what I did wrong. Did I push? anyway. I will just look here. Right, here they are. So here are some lemmas about the real numbers, which I've isolated. So here we go. So lemma. So I'm not going to talk about norm squared. This is going to be norm non-neg, and that's if x and y are real numbers, and that's 0 is less than or equal to x times x plus y times y. You see, we never use squares. There's no point using squares. I mean, if you need to raise something to the nth power, then sure. But if you're doing squares, so we've just proved this one. I'm now editing the wrong file. So let me take this back here. Here we are. So this I've just proved. This was this thing here. There. So now we have a proof. This is purely about real numbers, right? A theorem about reals. And there's several theorems about reals that we're missing. And so here we can just go apply norm non-neg. There. And now that lemma's been proved. But let me put all the lemmas I think we're missing. So the next one is norm x0 if. So again, I've got x and y real numbers. And I want to prove that x times x plus y times y equals 0. If and only if x equals 0 and y equals 0. That's again another really useful lemma. And to a mathematician, this is obvious, right? So this is whatever, begin, sorry, end. And the next thing I think we need is this lemma norm non-pos right. So there's 4 lemmas, and this is the third of them. This says x times x plus y times y less than or equal to 0. That should, yeah, less than or equal to 0. Then the conclusion is norm non-pos right. The conclusion is that y equals 0. There, and I've got a colon in the wrong place here. There, and the proof of norm non-pos right should be easy. We can. It suffices to prove that x equals 0 and y equals 0, because that's just obvious. Sim this. What do we? And now I should be able to rewrite. Now I can just rewrite norm x0 if. Oh no, I can't. I can rewrite. What can I rewrite? Oh, I can rewrite this way. Norm x0 if. There. And now my hypothesis is less than or equal to 0. I need to prove it's equal to 0, but I know it's greater than or equal to 0, so I can have h is norm neg xy. If I add that to the local context, norm non-neg, sorry. Now you see, what does Lean know? Lean now knows that it's less than or equal to 0 and that it's greater than or equal to 0. And the goal is to prove that it's equal to 0. And now this is an equation involving linear arithmetic. So you see, Lean can do that. So there's norm non-pos right. And then there's norm non-pos left, which is the other thing. There. And so let me just... norm non-pos left has got x and y in the reals. What is VS Code doing? We've got there, and h1 is that x times x plus y times y is less than or equal to 0. My VS Code's playing up. I want to deduce that x equals 0. And here I can just, what can I do? I can rewrite add comma h2 there, and then I imagine I can use norm pos. Oh, curses. There's an error. There's a typo there. If I rewrite add com now, and now I can probably exact norm pos right, norm non-pos right. Why don't I just apply it? What What happens if I apply it? Does that finish it? No, it doesn't know. What does it doesn't know? It doesn't know what y is. And it doesn't know about h2. X, h2. How about that? Right. So there is the proof of some real linear inequalities. This is the only one. This is the only one I haven't done. So how am I going to prove that? How am I going to prove non-zero? I think I'm going to have to split this one. X squared plus y squared is 0 if and only if x equals 0 and y equals 0. And I think this way is probably the hard way. So intro h. So now I've got x squared plus y squared is 0. So I guess I could you see I just happen to know a lemma. I know these things are the sum is equal to 0, so I can rewrite add x0. Add x0 what? You see add x0 if. Is that a thing? Maybe add x. I think this is what I want. Add x0 if primed at h. And now I've got something that's much more useful at h. Now you see, I think that simp might know that if x squared is 0, then x is 0. So simp, this might do this first goal. It did. And now this goal we know how to do. This one is apply mul self non-neg. I think. Yes, as is this one. So that's the difficult way done. And now this way here, we know that x equals 0 and we know that y is 0, and we have to prove that x times x plus y times y is 0. So this is much easier. We can just use. So let me show you a slow way of doing it. So how am I going to do this? I'm going to go intro h, and now I know that. So now I've got hypothesis h that says x is 0 and y is 0. So now I can do cases h with hx hy. So this is kind of a slow way through it. So now we know what x is and we know what y is. So now we can rewrite hx hy there. And now the goal has become something really easy. Now I bet the simplifier can solve this. So there we go. So there's a proof of that. But there's actually a much quicker way of doing this. Because really, instead of intro then cases you can do in one line. You can do this. You can do rintro hx hy. And now get rid of both of these, comma. There, so this still works and it's one line shorter. And now you see the goal before I did this, we had x equals 0 and y equals 0. So that we had that, that's one term, x equals 0 and y equals 0. And we split it up into two terms, which is what we need, because actually we want to do the substitution in. So that's one of the powers of rintro, is that you can introduce more than one thing at a time. But another really cool thing about rintro is there's no point having x, right? We're somehow defining the real number x to be equal to 0. And if actually we just defined x to be equal to 0, and instead of actually introducing x and saying, oh, and by the way, it's 0, we could just say, change all the x's to zeros. And you can do that with this, with ruffle. Ruffle means this is true by definition. So if you change hx to ruffle, then hx is now true by definition. If I remove it from here, then you can see we don't have an x at all now. And these x's in the goals, before the rintro, there was going to be an x in the goal. And after the rintro, the x has turned to 0. So you can put ruffle here as well. There. And so there's the proof the other way. So that's now proved everything I need about the real numbers. And now I should be able to finish these levels relatively quickly. Oh, I'm not sure that's true. Well, let's try it. So how are we going to do this one? If the norm squared of z is 0, then z is 0. So I guess we could rewrite, we could simp norm square and see what happens. And it's turned it into a question about real numbers, which is great because now we've got a bunch of lemmas about real numbers. So this one says that z re, yeah, I think maybe we should maybe tell it to use xif as well. because I don't really want to prove that z is there. There we go. Do you see, before I put x if, it said we have to prove it if and only if z was 0. But now we have, now this is purely a statement about real numbers. Z dot re and z dot in. These are real numbers. And is this one of the lemmas we proved? There you see we have this. So we can just do, it's this. It's exact norm x0 if xy. Where's my, there. Exact this. And it didn't work. Rotten luck. Oh, because there's no, it's something something. It's not x and y. It's z dot re and z dot in. I don't know what it is, so I'm just kind of saying, well, Lean can work that out. So now what? If the norm is positive, this is just a logic puzzle, right? This is just a logic puzzle. I think that here we don't want to be splitting into real and imaginary. Oh no, this is a question about real numbers anyway. Here we don't want to unfold norm square. We don't want to unfold it because I think you can formally, this is a question about the real numbers, and I think you can formally deduce norm square pos from the last two lemmas. So let's see if I can pull that off. How do I deduce? You see, there's some lemma about LT if and only. There's no. This should be done by tactic, right? I'm LE and NE. I know this lemma. This is a really useful lemma. LT if LE and NE. There it is. There. So what I've done here is I know the name of the lemma in the library that says A is less than B if and only if A is less than or equal to B, and A isn't equal to B. And so now we've got 0 nen norm square. And I wonder if I should rewrite. Maybe I should see if I can do all this with simp. Simp. What happens if I do this? Simp. I think I want to unravel the not equals as well. How are we doing so far? And now we need to know, what do we need to know? So let's tell it norm square x0. Norm square x0. How are we doing now, simp? And so now I think it needs to know norm square. It also needs to know norm square. Oh, I didn't need to tell it norm square x0 because it's already a simp lemma. This is what it needs to know. Norm square non-neg. That should help. Norm square non-neg. I wonder if that will actually do it. I've misspelled norm square non-neg. How are we doing? Now we've got to prove. Oh, now you see this really is. This, I really want to use norm square x0. Please use that. Honestly, it's a great idea. Oh, what have I done? I know you're in the list of, will it do it? It won't do it. Oh, it's because the equalities are the wrong way around. Oh, why don't I tell it to, maybe I should tell it to use it this way. Oh, now it's having a good long think. Oh, it's probably in a loop. Probably I shouldn't have done that. Let's do eccom. Yeah, look at that. That's kind of, I'm learning to tame the simplifier. So I've got the simplifier to solve this one. And what was going on here was I really thought I'd done it at this point here. But so far, Lean had managed to reduce it to this question, not 0 is norm squared z, if and only if not z is 0. And we have that here, right? We have kind of like the unknotted opposite of this. We know that the norm squared of z is 0 if and only if z is 0. So the simplifier, and we've told that to the simplifier, so the simplifier should do it, but the simplifier doesn't do it because this says 0 equals norm square, and this says norm square equals 0. It's a slightly different way around. And so, rotten luck. I have to insert eccom. And ecom is the statement, as you can see, is if A equals B, if and only if B equals A, and then the simplifier does it. I don't think there's much we can do about that. But anyway, now it's gone. And then finally, what do we need to know about this? Oops. Oh dear. Begin. Let's try simp norm square. See how far it gets. And this is exactly, this is apply mul self. You see, I really want to be doing a tactic, but I'm going to have to use mul self non-neg again. And I bet the same proof works here, right? I'm just going to copy and paste this proof in. There. So that has solved everything, yeah, apart from the dodgy imports. Dare I change this import now? If I change this to KB solutions, will everything break again? Last time I tried this, everything went haywire. No, it seems that everything's working now, but it still says that this uses sorry. For some reason, this is slightly more broken than it should be. But that's the only error is in the import. So there's something I've not quite done correctly. And now finally, let's prove that the complex numbers are a field. How long have we got? Great, we've done 34 minutes. We won't be long. So now how do we prove the complex numbers are a field? So here I've given no hints. So this is a slightly harsh. This is a slightly harsh level because I've given no indication at all as how we're going to do it. The first thing we need to do is to find the inverse of a complex number. So I guess that's pretty easy. The real part, I mean, we could do the calculation, right? So 1 over z. Let's just do the calculation. 1 over z equals, multiply top and bottom by the conjugate, is conj z over z times z bar, right? Z times conj z. So that's conj z over norm square z, right? But we haven't defined division, you see. So what's going on here? Why have we made some progress? So therefore that means, oh, what have I just done? There we go. So that's what 1 over z is. It's conj z over norm square z. And so the real part is what? You can see now, because we know the real part of conj z, right? So this is re z divided by norm square z. There. And the imaginary part is going to be im z over norm square z. And that's the inverse of a complex number. And out of interest, I never really thought about what would happen if that complex number was 0. And the reason I never really thought about it is because I know I'm never going to take the inverse of a complex number that's 0, because mathematicians don't do that. So I wrote down a formula that I knew would definitely be correct if z was a non-zero complex number. And if z is a non-zero complex number, remember its norm square is known to be non-zero. Do we know that? Yes, we do know that. That's one of the things we've just proved in here. The norm square of a complex number is non-zero. Where is it? That's the... Oh, we've never proved that. Let's prove that now, because this is going to be helpful, right? When we start doing divisions, this is something that should be in the game. Oh, this is interesting. I'm making the game better. This should be in the game. Lemma norm square ne0. There. This should say that the norm square of z is non-zero if and only if z is non-zero. There. And again, I should be able to prove it by the same sort of thing, by simp any. Maybe that will do it, actually. Does that do it? No, let's try end. Yes, have I got no errors? Yeah, I've got no errors, so that's done it. So now I've got norm square x0, norm square ne0 is going to be, I think that's the thing that we need, because we're going to be dividing by it at some point. So let's go. So there's the definition of inverse. And I didn't really think about what happened if I divided by 0. Because if you think about it, that would involve working out if z was 0, then this would be 0 over 0. And I don't really know what 0 over 0 is. But it's interesting that Lean hasn't rejected it. Lean's just like, yeah, okay, so the inverse of 0 has got real part 0 over 0 and imaginary part 0 over 0. So that's done this. And now this is just making inverse work. So what's the point about that? Example. I'm going to give an example of a complex number, and it's going to be 1 inverse. There, you see that works now. Or another example of a complex number would be 0 inverse, right? Because we just didn't bother, we don't know what that complex number is, right? But weirdly, it's definitely some kind of complex number. But we have no data. We have no data about this object. So I think before we prove it's a field, we should train simp, right? Otherwise, we're not going to get anywhere. Otherwise, we're just going to spend our entire time frustrated. So simp lemma invri, right, is the first thing we should do. I was kind of mean in this level. I didn't tell you that was what needed to be done. So simp lemma invri, what's that going to say? That will say the real part of z inverse equals the real part of z. I mean, it just says equals that. There, and the proof is REFL, right? And we'll never need these. And now there's an inv-im, right? Inv-im, which says that the imaginary part of z inverse is equal to what it's supposed to be. Minus, I've got it wrong, haven't I? That was interesting. I'm missing a sign here. Oh, no. Yes, I'm missing a sign. It was z bar. I'm missing a sign. So that's also true by definition. And now I think there's one other thing. One of the axioms for a field in Lean is that 0 is, I can see something coming that we haven't done. We haven't done this. We haven't proved that 0 is not equal to 1. We should have done that a long time ago. We should have done that a long time ago. So this is in the wrong there. When we defined 1, so this is right at the beginning. I re, I im, I mol I. Oh, this is even before I. We need. No, it's even before the map from the reals to the complexes. It's where we defined. It's where we defined 1. When we defined 1, here it is. Notation 1 for 1. Name the basic properties and tag them with simp. There's another basic property here, right? So this is lemma 0, 0 near. What was it called? Was it 0 near 1? Where's the level I'm actually supposed to be playing at this point? I'm supposed to be doing this. Yeah, 0 near 1. Let's call it. Now I've lost it. Let's call it 0 near 1. It's 0, 0 basic. Here we are. Lemma 0 near 1. And it is simply that the complex number 0 does not equal the complex number 1. There. Because that's somehow a fundamental fact about complex numbers. So why is that going to be true? I want to prove that after x. Have I got x diff at this point? Have I not got x? Maybe I should. Where is x? I'm proving all this with cases. Oh no, x revisited. I should have x somewhere. Well, let me just try it. Let's try x here. Oh no, let's do let's intro h, and let's rewrite x diff at h, because this is what I need. There, and it hasn't worked. So I don't need this lemma for a while. So where did I define x diff? There it is. So let me just stick that down here. So useful fact. There. And now after rewrite x diff at h, I'm imagining that the simplifier should be able to do this. Simp star at star. It did. Right, so maybe put in a better place. I'm not entirely sure where that goes. So let's get back to what we're supposed to be doing. So now I've proved that 0 isn't 1 because that's something we're going to use. So I think now we're going to be okay. So let's try proving. So now we're going to prove the complex numbers are a field. And what we have to do is these are the remaining axioms. So let's go. So this crazy axiom says that the inverse of 0 is 0, which is a bit surprising. I suppose what the first thing we should do is we should do ext, and then we should do simp, and then we should see what's left. And I don't know what's left. Nothing is left at all. So there we go. So that's the proof of that, ext simp. And so we've just proved, what's going on here? We've just managed to prove that the inverse of 0 is 0. Like, that's slightly weird. So maybe we should go back and have a look at what's going on here. The inverse of 0. What? So this number here. So this is the question. So here's an idle. This is nothing to do with the complexes. The question is, what's this number when z is 0? When z is 0, the real part of z is 0, and the norm square of z is 0. Let's do this. Let's do import tactic and data.real.basic. There. And let's go non-computable. And well, who knows? So let's try doing this. So let's do an example. So let's do the real number 0. Let's invert it, and let's see if it's 0. Oh, no. There. So here's a little puzzle. Is it true that the inverse of 0 is 0? So let's try. I don't know. Let's try to simplify it. This is true, right? So this is. Let's see what just happened there. So this is maybe a surprising thing. Imb 0. So what is this imb 0? Simp only imb 0. Imb 0 says that in any group with 0, the inverse of 0 is 0. And apparently the real numbers are a group with 0. And when you think about it, that's true, isn't it? If you imagine the real numbers and you forget addition and you just think about multiplication, the real numbers is the disjoint union of a group, namely the non-zero real numbers, and the number 0, which is this random extra thing thrown into this group, which doesn't obey the group axioms. And so why not just make the inverse of this thing equal to 0? Because we've got an inverse on the group. So there's a thing called a group with 0. The reals are a group with 0. And the way you extend inversion on a group to a group with 0 is you just find the inverse of 0 to be 0. So the inverse of 0 appears to be 0. And in this situation here, they're asking us to prove that the inverse of the complex number is 0. And the complex number 0 is 0. And that just follows, and that just follows from the fact that the inverse of 0 is 0 in the real numbers. Have I just confused something? What have I done? Sorry. Yeah, there I proved the inverse of the real number 0 is 0. And here we're proving that the inverse of the complex number 0 is 0 by reducing it to a question about real numbers. I guess after ext, we could try dsimp inv or something. We could try. Yeah, you can see what the goal is. The goal is something that somehow the simplifier is managing to do, because I think the simplifier knows that norm squared of 0 is 0. Let's put this back. Let's press on because I want to finish by 6. 0, no 1. We've just done that. 0, no 1. So that should be. I should be able to just do that. Great. And so what's happening so far? My only warnings are in the imports, which are fine because I'm not doing them today. And now this is the only thing left. And so what have we got to do? We've got to prove that for every, so let's intro z, And we've got to prove that if z is non-zero, then z times its inverse is 1. So this is the last axiom for a field we need. So let's intro hz. So we know that z isn't 0, and we need to prove that z times z inverse is 1. So this is an equality between two complex numbers. So I just want to do x simp. That's my instinct when I see this. And now we can see what the problem is. We've got to prove these two facts here, but this looks a bit scary actually. Yes, so according to chat person, the inv operation is defined on the whole of the complexes, and as a mathematician we don't really care what the inverse of 0 is, but the computer scientists have asked us to ensure that the inverse of 0 is 0 just for their bookkeeping. So now we're trying to prove the fundamental thing, right? This is the last thing left. For all complex numbers a, if a isn't 0, then a times its inverse is 1. And that's the axiom we need to prove that it's a field. So x simp is what normally does it, and you can see this is slightly problematic. This is like boss level stuff, because here so now we've got two goals. So maybe I'll just think about the first goal. There, let's be honest people. Oops. If I do that, now I've got no errors now. So here is the first problem, and that you can see what the problem is that we've got division by norm squared. This is purely a question about real numbers, but the ring tactic will not do it. So we've reduced it to a question about real numbers, but the ring tactic isn't doing it. The ring tactic just seems to tidy it up. And the reason the ring tactic isn't doing it is because this is not something about rings, right? Rings don't have inversion. Our goal has got division in. And so we need some other tactic that's like the ring tactic, but it knows about division. And we've divided by something. We've divided by some random thing. We divided by norm square of z. And how do we know that the norm square of z is non-zero? Well, we've proved that, right? This is the thing I went back to prove in level 4. This is kind of really crucial. Norm square ne 0, right? What we can look at our hypothesis. The hypothesis we have is that z isn't 0. That's of no use to us. The hypothesis that z isn't 0. Z isn't 0 translates as a really stupid. Either x isn't 0 or x is 0 and y isn't 0, right? That's what z isn't 0 boils down to. But if we rewrite this thing here as hz, then hz becomes a much more useful. Oh, it didn't work. Hard luck. Norm square x 0. I thought I had that. I thought I just. Oh, I'm not importing it. I'll have to put your solutions there. Hopefully, if I do this, then all the bars disappear. Great. We've got one complaint that we've got a dodgy import, and we still haven't got a norm square x 0. What a shame. Oh no, there it is. Oh, it's rewriting the other way, of course. Perfect. There. And so now when we do all this, now if you look at what's going on, we're dividing by this real number, norm squared of z, but in the context is this concept that the norm squared of z is non-zero. So that means, so now we're somehow in a situation where we can use another, there's another tactic called field simp. So we do field simp, and we tell it 8z. And let's see what field simp's made of it. Oh, it hasn't done it. Ooh. Oh, rotten luck. Now we're in trouble. Because I don't know what to do if field sim doesn't do it. It might get painful. Might be worth going back to my laptop, I think. I thought I had some cunning little way of doing this. What have I done wrong? Z.norm square. Oh, that's right. I couldn't get this to work. We have to unfold. Yeah, I don't really understand why field sims won't pick up on this. But we need to turn this into, we need to do this. We need to actually unfold norm square. everywhere. There. So now we've eliminated norm squirt as well, and now when I do field sim HC, yeah. So now what's the goal before the field sim? You see, this is now there. Now there's no norm square. This is completely about the two real numbers, the real part of z and the imaginary part of z, and we're dividing by something, and we're not entirely sure that this thing is non-zero, except we do know it's zero. We've added it into the context. So now field simp hz, you see it clears the denominators. So this tactic, this clears denominators. There. And now we've cleared denominators. This is now a question with no division in. So now this is a question which the ring tactic will solve. There, and as you see, it's solved it. And in fact, that little run there, I can make that exactly those tactics there will solve this sorry here, I suspect. So I can delete that sorry and put this. Oh, what have I just done? Deleted more than I bargained for. If I put a semicolon here, it's compiled. There we go. So we have no errors, and we have one warning, and that one warning is because there's some import that's gone wrong. And so that is the proof that the complex numbers are a field. And now we could finish off by, we've never defined division, so let's do this in there, sort of finale here. Let's define div. There. So so in MathLib this is how it's defined. If I define div for z and w complex numbers, and z over w, so this is going to be z divided by w, and I'm just going to define this to be z times w inverse, right? Because we've defined inverses, so now I can define division using inverses. So instance has div c there, complex dot div there, and this is notation. So now we can finally, this is before here we haven't ever been able to divide complex numbers. So here's an example then. I claim that the complex number 1 divided by the complex number 0, I don't have to put any of the others because the others Lean will just guess, is 0. So why is that? Well, this is an equality between complex numbers, so I should probably check on real and imaginary parts. And if I check on real and imaginary parts, what goals have I got? So I think that the simplifier knows. Oh, the simplifier might not know, but I see. The simplifier doesn't know about. Let's try it anyway. Let's try simp div. Let's just tell the simplifier to use div, and lo and behold, it does it. So this is a proof. This is a complete proof that 1 divided by 0 is 0. Because what's happening is that in Lean they demand that when we're extending, we extend division on a field. Division is defined. Division and inverses are defined on the whole field, and anything divided by 0 is just defined to be 0. And it doesn't cause a problem because mathematicians never divide by 0. You see, when we prove an interesting maths theorem here, like we want to prove this, a times its inverse is 1, but that's only true when a isn't 0. So this is we're only making an assertion about the inverse of a when a is non-zero. So, you know, when you divide things by 0, kind of random stuff happens that can, you know, they make computer scientists happy. But mathematicians, you know, they can take it or leave it. As far as I'm concerned, this isn't mathematics. So that can go. But when you make the complex as a field, that's how they want you to set it up. You know, they demand that you prove that the inverse of 0 is 0, because for them they just think that that's a more convenient way of axiomatizing fields. Right, and I think that's it. If there's any questions, I'll try and take them on the chat, and if not, I'll head over to the Discord, and we can do some stuff there. And thank you very much. I'll stop recording.